So I've got my new Infranor BR3 motor here. It's an interesting design. It's kind of pancake-like, very flat. It's got good mounting bolt holes, coils around the outside with good heat dissipation. There's some looks like fins and black anodized, good for heat radiation. The magnets are on the inside. It's a 20-pole or 10-pole pair motor. Nice shaft and bearing, commutating encoder on the back. That's incremental with Halls. And we'll take a look at some interesting characteristics about this motor. BR series for robotics, accuracy for high precision applications. Actually, I'm going to show off some new features for getting the best velocity regulation, so better than 1%. We're going to shoot for 0.1%, of course. And this motor is going to help me get there because it's got some good inertia characteristics. Kilogram meters squared times 10 to the minus 3, and I've got the BR3, so that's 0.1. That's about 1 kilogram centimeter squared, so a little more than some of my other motors. These are designed to operate off 48 volts. That's nice. I've got some stall current, 18 amps. This thing had a very high peak current. Low inductance, low resistance, 200 microhenries, 0.2 ohms, so not a lot of energy lost in the motor. This motor had a 58 amp peak rating, but continuous is more down around 10 amps or so. So we'll take a look at the drive. I'm going to use the Nano EtherCAT Plus drive. It does 70 amps peak, so we can hit 58 with no problem. We only really need 10 continuous, so well within the keep the drive cool range, running it at 10 amps with the heat plate mounted to, say, the box or a metal frame. So I got the motor specification for motor powers, UVW, and earth. The case goes to earth, so you can connect UVW windings, red, gray, blue, look more like black, and then the yellow, green for earth, so the case finds a good path to earth. And when you mount the motor to the frame of the machine, you get a good path to earth. If it's a vehicle, of course, the frame of the vehicle is like earth, even though it's not touching earth. You got your basic AA naught, BB naught, ZZ naught, which is index, +5 and ground. You've got a UVW Hall plus. I'm not using the Hall minus. I'm not sure what the transmit and receive is. I haven't figured that out yet, but I guess you can talk to this encoder. And there were also a couple wires for motor temperature sensing, so 55 ohms at room temperature. I'm not sure what the characteristic of that temperature sensor is, but we can figure it out if you need it. You don't need it. We're going to protect the drive or the motor by setting the current limits I2T algorithm. So just your basic, how do you wire stuff, UVW Halls, +5 and ground, AA naught, BB naught, XX naught. Also have UVW Halls, but the frame, right, this goes to earth at the drive, so pin 1 goes to earth because you connect earth at the drive, and the frame goes to earth. And there's a shield on the feedback, so if you have a shield, the only thing worse than not having a shield is having a shield and not connecting it to earth. Or if you connect your feedback shield to the motor case, that would be bad, but Infranor would never do that, so they're good. So here's the motor, and it came with little cables on it. We put the connector for the Copley, and the guy sent me a brochure. So we're going to take a look at CME 2 up and running, connected to the motor here. Just the basic configuration is brushless rotary. There's no brake on this one. Incremental encoder with Halls. It's 2048, which is line count multiplied by 4 is 8192 counts per rev. And don't ignore your feedback. If you had a brake, you could come to a controlled stop. I'm just going to do position mode, software programmed, or leave it in the EtherCAT mode. That's fine. Sinusoidal commutation, emulated output if you need it. Wow, all that on a nano. That's pretty good. Not bad for a little tiny drive. Your basic data, kilograms, centimeters squared, 20 poles. Huge torque peak, a lot smaller, continuous. Torque constant was given in Newton meters per amp RMS, entered, converts to about 0.1. Same thing with volts per radians per second. So about 10 volts per kRPM. 48 volts, maybe 4,000 RPM. Sounds about right, little IR drop. So 48 volts, you're not going to hit the 6,000, but the motor's rated for a little less anyways. So we're good. Current loop tuning came out, about a kilohertz of current loop bandwidth. So there's the continuous rating of the motor. And I just, 3 times the continuous is good for peak, but you could do 58 if you want. That would be the 70 amp version of the Nano. And velocity loop was tuned up, and you can see the maximum theoretical speed. We're going to be less than that, but if you go 3,000 RPM and you want 0.1%, 3,000 RPM times 0.1 divided by 100 for a percentage, that's 3 RPM. So that's what we're going to key in on for the after the loops are tuned. We're going to get velocity regulation. And oh, by the way, when you're in a position mode, you get much better velocity regulation. You could be in a velocity mode and you've got some filters to filter out any resonances or to crank up the gains. You can have a higher current velocity loop bandwidth and try to correct for any disturbances that come in, or you can not excite disturbances in the first place. Really depends on the construction of your motor. This motor has good inertia. It's pretty smooth. There's not a lot of unnecessary cog in the motor. There's some feed forward terms for the velocity loop if you want to get that around 0 while you're moving in velocity mode. But we're going to use the position mode around the velocity loop. So this is in terms of counts per second. And there is also, besides the proportional gain, there's a feed forward term for this too. And that feeds into the velocity loop to make a correction. And so there's the VFF. You could use some acceleration feed forward during acceleration, but I'm just going to let it settle into speed and, not mess with the acceleration feed forward. That tends to fight with the integral in the velocity loop. So I'm just going to let the integral do its thing. So for the basic move here, we're going to do 10 revs divided by 5 revs. We're going to look at the profile velocity following your actual current. And we're going to look at the ugly, unfiltered velocity coming from the encoder. This has the sampling errors, and it's just the raw data. That's not really what's going on. It's impossible in between samples to go from, 6, 6, 6, and then 7, so the change is infinite. Really, the motor's going much smoother than that. So we'll take a look at some realities of the velocity, but first we'll look at the unfiltered velocity used to close the velocity loop. So we're going to make this move, trajectory move 3,000 RPM, and we're going to shoot for the 1%, 0.1% or 3 RPM within 10 milliseconds. So let's give it a whirl. Yeah, the gains are already adjusted. Didn't go crazy with the position loop. Just tuned up for nice stiffness in the velocity loop, and I just left the pole at the default. So let's take a look at the move. So that's 5 revs, 3000 RPM. And we're going to monitor the velocity outside of the tracking window. So, before the move, we're good. That's 0 velocity. That doesn't count. But while we're moving, we can't seem to get within this window. And then after we move, we got a little settling and a little vibration here. But let's zoom in to the command and actual. So you can see the command in magenta is perfect. And then you got all this noisy stuff, which is the sampling. You're talking about samples of an encoder every 250 microseconds. So you could have a sample that brings you outside of this window. It's a quantization or sampling error. But really what you're interested in is kind of the average of these pulses. So what we're going to do is turn on the filtered velocity, and we'll take a look at the filtered velocity, which is the actual motor velocity as displayed in the scope. It won't look so noisy. It'll look a little cleaner because it goes through a filter and it averages it out. We know it's impossible to go from one speed to another in 0 time. So you can see, yes, it's much tighter, right? So on average, you're following the command. You got a little bit of, not sure what that is, exceeding, but you're still tracking. Although it's a little sensitive to this. Sometimes when we're flying along, we get a little bit more error. Yeah, so this lasted a little longer. And I think I had it right on the edge of 0.1%. Yeah, well, let's go down to better than 0.1%. It's a claim I'm not trying to claim, better than 0.1%, but there we go. So if we're trying to push it to better than 0.1%, you can see that you do fall out. If you zoom in, left click, drag, drop, you can see that even with an averaging or a filtering, you still fall out of the less than 0.1% window occasionally. These are still artifacts of the averaging. The command is perfect though, so just keep that in mind. In a position mode, we're trying to do that count over time, right? So if we look at the following error, that's really our main interest here, is how flat is this? So we're holding position over time, plus or minus, well, 1 count or plus or minus 2 counts occasionally. So that makes you fall out of the tracking just by its quantization or the resolution of the feedback device here. So let's take a look at the commanded velocity, because we're not in a velocity mode here. We're in a position mode doing velocity profiling. So let's take a look. And we're going to see if that tightens it up a little bit. Reading. It's subjective. Still you get the position error falling out. But it is a slight improvement. And then with the 0.1% or 3 RPM out of 3000, we should get with both these options. These are new options for CME, which allow us to control the algorithm for the bit to ensure that we see, what's really there, right? You don't want to get false alarms that we've fallen out of the window. You want a nice alarm. And so during acceleration, you get out of the tracking window. There's a little overshoot here. Maybe we could do a little different tuning, but whether you come in below or above, you still got to settle out. And then same thing when you're decelerating, you get a little overshoot, and then it settles in. So you're outside of the tracking window during accel and decel. For the gains, I use 16384 for the velocity feed forward. That brings the following error within tracking here, and didn't overdo the integral. If you overdo the integral, it just takes longer to settle, whether you're settling to velocity or settling to speed.